Our first speaker is Raman Sullivan. Ryan did his PhD in atmospheric chemistry at UCSD. Now he's a professor of environmental chemistry at Carnegie Mellon. His lab studies the reactions of chemicals in the environment, their consequences for human health, cloud formation, and climate. When he isn't playing volleyball or lifting weights in an Olympic fashion, he also works on using aerosol chemistry as a new way to purify water of persistent chemical toxins. Please make it very loud for Raman Sullivan.
Hey everyone, thanks so much for having me. Sorry, I was just trying as usual to fight with Zoom. Can you see my screen? Good, okay, great. So I'm gonna be talking about wildfires and hopefully telling you some things about wildfires that you are less familiar with. I realize, especially if you are living in San Diego or in the West Coast, this year has been a particularly bad year for wildfires. I'm afraid that the West Coast is really just sort of permanently fucked by wildfires thanks to climate change. I moved to San Diego in 2003 to start my PhD there. That was the first year of sort of really bad wildfires in the San Diego area, so people were really not prepared. I was very unprepared coming from Toronto, which never has wildfires. I didn't have a car. I was living in UTC without a car, which really sucked. I didn't know if I had to evacuate or not because everything is called Scripps around there. So like constantly on the news, it was like Scripps Ranch and Scripps this, and I was like, is that me? Like, so if you have been experiencing the wildfires this year, I feel you. Even though my lab studies wildfire smoke chemistry all the time, I hate the smell of wood smoke. I was camping recently. It's the only trip I've taken all summer because of COVID. And it was much needed. It was this really nice state campground in Pennsylvania. But I would walk by people in the middle of the day, like a hot, late August day, and with this campfire roaring, just filling up the canyon we were in with smoke, like unnecessarily. And actually, wildfire smoke is some of the most toxic particulate matter there is. We still don't know exactly why it's so toxic. We have some hints, but you definitely need to avoid it if at all possible. So we're going to be talking about how wildfires can actually make ice and change the properties of clouds and climate, how they can drive additional chemistry because they release these reactive salts into the atmosphere, and then also how fires can release synthetic toxic chemicals as well. So the image in the background here, this is a sawgrass fire, which isn't so different than some fuels that might burn in San Diego. San Diego has a lot of chaparral. Like that's a lot of what burned in that 2003 fire that I lived through. And I just point this out because a lot of people, especially maybe not if they're from the West or East Coast, they think of wildfires as like, when the forest, like the pine forest burns. And that's true, but there are many other types of fires. And actually these types of fires with tall grasses and shrubs are much more globally important and prevalent than when trees in mature forests burn. All right, so I chose to start with this diagram, and I hope when I put this diagram up, maybe you kind of like got a like, oh my God reaction, like there's so much going on here, because that's sort of the point. This is where I live. This is where my field of atmospheric chemistry lives, trying to understand all these important processes and effects and impacts that particles have on the atmosphere. So we have particles, that are emitted from the atmosphere, such as from the land, such as from wildfires or the ocean. They do all sorts of stuff in the atmosphere. They interact with clouds. They make clouds. They change clouds. They can cause precipitation. So they come back down to the land. So there's a lot going on. The main takeaways that we'll be talking about today are that all of this chemistry in the atmosphere can make new additional secondary pollutants. So it's not just the initial pollutants that come out with the fire. It's also all this additional secondary chemistry that makes even more toxic pollution. And then also how particles interact with clouds, change the properties of clouds, and are actually a big factor in climate change, but are one of the most uncertain parts of climate change. So in my group, we focus a lot on particles from volcanoes. I won't be talking about that today, and also a lot on biomass burning, which is a fancy word for basically emissions from wildfires. Here's a satellite image of smoke from wildfires in Indonesia passing over Singapore. I chose this image because I gave a talk in Singapore last year, and so Singapore, very wealthy, pretty clean air locally, but often severely impacted by wildfires. So the smoke can travel really long distances. The smoke from the California wildfires a few weeks ago reached Pittsburgh in Pennsylvania, for example, and did cause some effects on our local weather and climate. Smoke from Asia can cross the Pacific Ocean and reach you guys in the West Coast, for example. So it really has some really important long range as well as short range effects on the atmosphere and climate and on health. All right, so particles are really special because they do things in the atmosphere that would not take place in the gas phase alone. So particles act as these unintended catalysts, so they cause chemical reactions to proceed much more quickly than they would without the particle. They can even cause reactions that would only happen if there's a particle present. And one reaction that we'll talk about today, and I promise I'll keep the chemistry pretty simple, is this reaction of this molecule here, N2O5, what happens to it when it bumps into a particle, because it's really important to know if it makes nitric acid or this funny molecule, nitrile chloride, because this one will go on to make a lot more ozone and pollution, and this one will actually turn off or shut down ozone formation. So particles, they do chemistry that makes more particulate matter. All particulate matter is toxic to some degree. It changes the chemistry of the atmosphere, how much oxidants you have, how much ozone you have, formation of smog. And this chemistry also changes the properties, the chemical composition of the particles as well, which has important effects for the other impacts that particles have on the atmosphere, on us, and on clouds and climate. And then every little cloud droplet or ice crystal is formed on a particle seed, doesn't happen from water vapor on its own. And as we add more particles into clouds, into the atmosphere, or change the types of particles that we're putting into the atmosphere, we can change the properties of clouds. So what you're seeing here is a satellite image, and these bright streaks here are ship tracks. So these are the emissions from ships in open waters where they can burn really dirty, low-grade bunker fuel, which puts out a lot of particles and other emissions. And so you're adding more particles to the cloud, and you're basically taking the same amount of water vapor in the cloud, but spreading it over more and more smaller cloud droplets, and that makes the cloud brighter. And this can actually be an important offset to the global warming caused by greenhouse gases, because now the clouds are more reflective and they're going to reflect more incoming solar radiation and provide some offset cooling to the warming caused by the greenhouse gases. So these effects of particles on clouds, they change the cloud microphysics. They can also, if they're ice nucleating particles, they can make the cloud freeze, and that's the best way to make a cloud precipitate. Can offset some of the warming caused by greenhouse gases, but this is where the largest uncertainties in our understanding of climate change exist, is how particles are interacting with clouds and changing climate, especially for the ice nucleating particles, which happens to be what my group focuses on because they are such a big and important sort of black box, a mystery, but we are making a lot of progress recently in understanding them. So this is a little more detail. What you're seeing here, this is a nice figure actually from my postdoc advisor, Paul DeMott, it really matters if the particles in the atmosphere tend to make more liquid cloud droplets or make more ice crystals. If you have mostly liquid cloud droplets, then you don't tend to get, the clouds don't rise as high, you don't tend to get the big convective anvils, you get less precipitation, you have, and then if you are adding more ice nucleating particles, and the best source of ice nucleating particles is from the desert and also the oceans, but what I'll show you today is that wildfires can also put ice nucleating particles into the atmosphere, then you really start to change the properties of clouds. So you can cause a lot of freezing in the cloud. That will cause a lot of precipitation. That's where you get the big convective storms from. That's also where you get lightning. Some part of the cloud needs to be frozen to get lightning, which is also a major trigger for wildfires. So you can really start to play with the energy budget, how much solar radiation the clouds are reflecting and how much outgoing terrestrial infrared radiation the clouds are absorbing. And so that's why we really care about understanding the sources of ice nucleating particles and their behavior in the atmosphere. This is figure showing what fraction of clouds that produced rain were frozen or not. I don't know why they chose red to represent the fraction of clouds that were frozen, but the point is that over land, you see that it's almost all red, which means that most of the precipitation over land actually comes from clouds that are frozen. You just don't tend to realize that because by the time the ice crystals reach you at the surface, they've gone through a big temperature gradient and they've melted, and it just looks like rain, but it's cold rain, and it's initiated by these ice nucleating particles, which again is why understanding the sources and behavior of ice nucleating particles in the atmosphere is so important to understand clouds and precipitation and climate change. So the question my group has been grappling with for quite a while, but we've made a lot of progress recently and finally got some big papers out on this, is answering this question: can you make ice from fire? So our wildfires, which can be very convective and the smoke can rise very high into the atmosphere, can actually punch its way all the way up into the next layer of the atmosphere called the stratosphere, which is difficult to do. Can these wildfires introduce ice nucleating particles into the atmosphere, which could dramatically change the properties of clouds, whether or not the cloud precipitates or not, and the effects of human activities, because humans are causing wildfires to be more severe and more frequent, the effects of human activities on climate change. All right, so I just wanted to talk a little bit about wildfires. I'm sure you are well aware of this, but here is a nice compilation of data. Wildfires are getting more severe, especially in the last 2 decades, and it is driven by climate change. It is driven by human activities because we are causing droughts to be longer and much more severe. You guys are well aware of this if you're in San Diego. Also, there's other effects too, right? San Diego is really expensive. So more people have been moving to eastern San Diego County, where it's not quite so astronomically expensive, but now you're living in a more fire-prone area. It's also hotter there, which means you need to use more air conditioning, which means you need to burn more fossil fuels if that's your source of energy for the air conditioning. So you get this sort of positive feedback that's also involved there. So this is just data showing, the wildfires are getting larger and more frequent and causing more damage, burning more area, and that climate change is largely responsible. So about half of the area that has been burned by wildfires recently is attributed due to climate change. Or in other words, if we hadn't caused climate change, we would have had about half less of the area burned by wildfires that we're experiencing in the last couple of years. This may be unfamiliar to you because it's more related to the mountain regions in the Southwest and not so much the coastal regions. But the pine bark beetle infestations have killed massive swaths of forests in the western US. When I was actually driving $1 million of equipment in a cargo van back from Riverside back to Colorado, because we were doing experiments in Riverside, I decided to make some stops through southern Utah and northern Arizona, which if you haven't been there is like really, really beautiful. You just spit in any direction and you hit like another national park or forest. So I went to the north rim of the Grand Canyon, although I thought Zion was actually more impressive than the north rim of the Grand Canyon. And while you're driving there, I forget the name of the national forest you're driving through, it's just all this brown, dead swaths of forest because these bark beetles are damaging the bark of the tree, which is like the outer protective layer of the tree, and causing all these trees to die. And now they're like kindling, just waiting to light up. And one of the reasons this is happening is the bark beetles only get killed in the winter if the temperatures drop really low for long periods of time. So, below 0 degrees Celsius. So I know in San Diego, you freak out if it's like 10, 15 degrees Celsius, you get the parkas out. That's like, 40, 45 degrees Celsius or Fahrenheit. So much colder than that. It has to be much colder than that for a week or more continuously for the bark beetles to die off. And that's just not happening very much anymore because of climate change. So there's another factor. So there's so many factors and feedbacks that are involved. And that's sort of what environmental science is all about. I'm teaching a course in environmental science. And that's what I want my class to take away from this. That it's really important to understand these complex interactions and these feedbacks in environmental systems, and then understand how are humans interfering with those systems and altering them, and what are the consequences of that, and what might we do to reduce that or reverse it or prevent it going forward. Also important to note, there's been a lot of discussion about this, which is good to see. Wildfires are a natural process. They're an important one. There's a whole field called fire ecology, which is really interesting to look into. But wildfires are really important because they drive what's called succession in ecosystems. So when you have a wildfire, depending on how severe it is, this actually adds a lot of nutrients to the soil. And then these pioneer species, the microbes, the fungi, the lichen, the moss, the small herbs, they move in quickly and use those nutrients that just became available. And so you have this whole period of succession. Also, a lot of species, for example, pine trees, they need fire in order for the pine cones to release their seeds and germinate so that they can reproduce and populate. And so if that fire isn't occurring, then that dramatically affects ecosystems because it's supposed to occur naturally. And in the US, it has been government policy for the last century to aggressively prevent forest fires. And that has been interfering with natural fire succession. It also causes fuel to build up to much higher levels than it otherwise would. But I don't want you to think that I am agreeing with what Trump says that, California needs to like sweep their forest floors more often. That is not true. It is definitely driven by climate change, but there are other factors going on as well. That's sort of what I want to point out here. It is mostly due to climate change, but there are other things to consider. And the takeaway from this is that fire is a natural and important process that is supposed to happen in a lot of ecosystems, and we have been preventing it, and that's an issue. Okay, so my lab studies biomass burning wildfires, which one of the reasons it takes us so long to like get papers out on this is it's really complex because you're basically taking this unrefined fuel, wood, tall grasses, and we burn it in a pan to try to simulate how things burn in the environment, which is totally uncontrolled. You're not like in a high efficiency stove or anything. And the emissions that come out are really complex. So you have things like graphitic black carbon soot and a bunch of reactive gases and polycyclic aromatic hydrocarbons, which are carcinogens, and organic carbon molecules. And then we also study the ash that remains, and that was actually really important. That gave us some important clues. And this ash can get lofted in the atmosphere because the wildfires are so intense, they cause so much convection that you can actually get these big ash particles to loft. I'm sure you've found ash on your car, recently because of the wildfires. So what we're going to talk about today are two sort of overlooked aspects of biomass burning, which are the mineral particles that are present and the chloride salts that are present, and what are the consequences of those species in this complex smoke. So if we look at particles collected from the smoke from our lab experiments under an electron beam, so we can look at really, really small particles. So you notice the scale bar here is 500 nanometers, so a half a micron. We see that the aerosol, the particles are really complex. No particle is like another one. We've got these tar balls. We've got some kind of organic carbon shell around another type of particle. Here's those chloride salts glommed onto some graphitic soot with a tar ball as well. Here's a mineral oxide particle. So there's lots of stuff going on, and each of these can have very different chemistry and different cloud nucleation properties, for example. I'm just gonna move my cat off my laptop and bring him over here. Maybe you can see him. He loves to sleep on my laptop, which causes the laptop to overheat, which is like not so good for the laptop. This is Apollo. He usually Zoom bombs, but I think he's in sleeping mode, but you get to meet him anyways. Okay, so I just want to show you how we actually measure the ice nucleation properties of the particles. So we developed a new method using a technique called microfluidics. So basically, we use soft lithography to create this array that we can trap 600 little droplets in, and then send them through a cooling cycle and measure at what temperature does each droplet freeze at, and that tells us about the ice nucleation properties of the particles in that droplet. So here is what each one of these microwells looks like, and the droplet's going to get trapped in here. And here is how it works. So this is a little video. So right now the device is filled with oil, and then, whoops, that wasn't supposed to happen. And then we're going to flow in water that contains particles of interest suspended in them. And so we fill up all of the wells with water with these particles of interest. And then we backflow oil in again. And you'll see that we shear off a little droplet in each of the wells. So we have this whole array over here. You can see hundreds of these droplets isolated in these wells. And then we start to cool. And when each one freezes, it turns white. And we use an algorithm to detect when each one freezes, and we get the freezing temperature spectrum. So we take this chip with all these droplets, put it on a cold plate, send it through a cooling cycle, And then this is what the data looks like. So this is the fraction of droplets that froze as we cooled. And one nice thing about the microfluidics is it allows us to access much colder temperatures than the conventional techniques that we were using before, which is important because a lot of the ice nucleation activity from the biomass burning aerosol, the wildfire smoke, occurs in this region, so we wouldn't be able to measure it if we use the conventional technique. But when we use the microfluidic technique that we invented, we can access those temperatures. This is probably the most complicated plot I'll show you. I'm not going to like walk you through all the data, but this is our assessment of the ice nucleation properties of the particles in the smoke. And so this is the raw data, and then we convert it to this form, which is more useful. And basically, a higher number on the y-axis means that it's a better ice nucleant, a stronger ice nucleant, and it's plotted versus temperature. And the takeaway is that the biomass burning aerosol and the ash that remains both contain ice nucleants. And the aerosol and the ash from the tall grass species has better ice nucleants than when we burn wood like birch or ponderosa pine. And the ice nucleation properties of the aerosol and the ash are very similar to other types of mineral containing particles like quartz or domestic ash when you burn stuff in a high efficiency oven to heat your home, for example. And that connection to other mineral containing particle types was an important finding, gave us an important clue. We then took the ash and put it under an X-ray beam, and the atoms in the material cause a diffraction pattern of the X-rays. So you get this diffraction pattern. And when you have very crystalline material, so very well-ordered material where all the atoms are in a repeating position, you get a really nice diffraction pattern, and that's where you get these nice strong diffraction peaks. And when you don't have a well-ordered material, it's what we call amorphous or disordered. You don't see that nice diffraction pattern. You just kind of get this blah. And so it turns out that when you burn tall grasses, they have better ice nucleants in them, and they have more crystalline material. When you burn something like birch wood, you get weak ice nucleation activity, and you don't get crystalline material. And that all makes sense because it is known that crystalline phases tend to be better ice nucleants than amorphous crap is. And so we were basically able to bring all this together and basically tell our community that, hey, we've finally helped unravel the sort of a big mystery in ice nucleation, why sometimes you get ice nucleants from biomass burning when you burn one fuel, and other times you don't get biomass burning. It seems to be, you can predict it by, if you look at the composition of the original fuel, tall grasses tend to be enriched in mineral forming elements like calcium or aluminum or iron or silicon, and birch is not. And that explains why when you burn tall grasses, you make a bunch of minerals, crystalline minerals, and they have ice nucleation activity. And so everything kind of like came full circle, but it took us years of working on these messy systems in order to figure that out. The other story with sort of an overlooked aspect of biomass burning smoke is those salts that I pointed out in the biomass burning smoke. They can be reactive, and they can drive additional chemistry, especially far away from the original source of the smoke. So what happens at night is nitrogen oxides, which comes from combustion. So all of your vehicles are putting out a little bit of nitrogen oxide. It makes ozone. It also reacts with ozone and makes this nitrate radical. At night, they get together and form this species here, which is pretty stable. But if it bumps into a particle that contains water, it can undergo a chemical reaction. And it can just make nitric acid, which is a sink for nitrogen oxides, which actually shuts down ozone production. So, but if there's chloride in that particle, like in these particles in the smoke, instead it can make nitrile chloride. And that's important because when the sun rises in the morning, that will promptly photolyze by the sunlight, and you'll get this potent oxidant radical, which is going to make a whole bunch more pollution. And you'll regenerate nitrogen oxides, which goes on to make more ozone, and you get secondary particulate matter. So this is particulate matter that forms from chemical reactions in the atmosphere. And remember that all particulate matter is toxic to some degree. So we are basically, if we go this channel, we are making more air pollution and increasing the toxic impacts on our health, for example, from that air pollution. The bottom line is that we demonstrated by doing laboratory experiments on real emissions from real fuels. I actually sent my students to the National Alligator Refuge in North Carolina, because we were running out of fuels. And when they came back with all the fuels, I realized why our collaborators weren't sending us fuels anymore, because the names sawgrass and cutgrass that we were interested in are very literally named. The blades are serrated and they will cut you, and it's wetlands, so it's swampy. And so it was kind of a miserable experience, and they never asked to do it again. But it was really important that they got those fuels, because the whole point of my lab is we want to sort of bring the environment into the lab so we can study very realistic, complex systems, but under a controlled laboratory condition. And so the bottom line is that we were the first ones to explore whether or not this chemistry can actually happen in real biomass burning smoke, and it can. And so now the atmospheric chemistry community is aware of that and can start to model or predict what might the consequences of this be that we were sort of not aware of or overlooking before. Last thing related to combustion is in your homes, and actually California is largely responsible for this. Decades ago, California was very concerned with couches catching on fire, although it wasn't really an issue, but they were concerned. And so they mandated that large amounts of flame retardant chemicals be put into upholstery, into couch foam and other upholstered goods. But those flame retardants, like these guys here, are toxic themselves. You have to put a lot of them into a couch, and it still doesn't do a great job of actually retarding the fire. And people are, they get into the dust in your house, and people are exposed to these chemicals. Babies especially are exposed because they're crawling around and they have a small body mass. Cats as well can get and dogs can get very exposed to these as well. And humans also get exposed, but at lower levels because we're not crawling around usually. So these chemicals are toxic. California has revised their regulation. They no longer require this. And in fact, they will probably put some label, from some proposition warning you if these chemicals are there. But it was actually California that initially drove the reason why they use flame retardants. And because California's market is so big, when California makes a decision, sort of the rest of the US tends to go that way as well. So actually what we wanted to study is, we know there's all these flame retardants in the foam. We know they don't do a great job of actually preventing the fire. So if a house catches fire in a fire, these couches with the flame retardants are going to burn. Our hypothesis is that the addition of these flame retardants is actually going to make the emissions from the couch when it burns even more toxic. And so you could get all of these secondary toxins produced. Many of them are carcinogens, for example. And the bottom line, we're still working on this, is our preliminary data is that we actually see when we burn different foam samples with or without flame retardants, if they contain flame retardants, we actually see the original intact flame retardants coming out in the emissions, and we know those are toxic, and we do see evidence for other new secondary toxics being produced as well. So this would mean that putting flame retardants into couches and other consumer products has even worse consequences than we realize, because the original chemicals are toxic. They aren't really doing a good job of preventing the fire and the couch burning. And then when it does burn, they release the original flame retardants, which are toxic, and they produce new toxins as well. Okay, last little bit of science is how my lab, which is the background you've been seeing this whole time behind me, studies particles by trapping them in a laser beam. It's called optical tweezers. I heard you already had a nerd night a while ago about optical tweezers. It was probably about using optical tweezers to study biology, which is very commonly done. Using optical tweezers to study aerosol particles levitated in a light beam is sort of more niche and a little more rare, though it's catching on. But it allows us to do really cool, really powerful experiments. It was a very new research direction for me to take when I started my position at Carnegie Mellon, but I'm really glad I did, because it's been really worthwhile and a lot of fun and very productive. So the power of optical tweezers. So we basically shine a laser beam through this microscope objective. Here's Kyle, who built the system and was an awesome PhD student of mine. It forms this very focused beam of light on the other side of the microscope objective, and that's where the particle gets trapped. The particle acts as this optical resonator. And so some light is scattered It's called Raman Scattering, which is this complex forbidden transition, but it still happens because quantum mechanics are weird. And when you say forbidden, it doesn't mean never, it just means rare. So these Raman scattered photons are emitted, they're excited by the laser beam, and some of them get trapped and they form this staining wave and they resonate around the circumference of the droplet. And that causes these very sharp peaks in the Raman spectrum. So this is the vibrational mode of water. And this is the vibrational mode of some oil, organic carbon oil, very hydrophobic oil. But these sharp peaks, those are the whispering gallery modes. And by analyzing these positions and how they change in the spectrum, this is the secret sauce that makes this technique really powerful. We can determine the size of micron-sized droplets to a nanometer and do lots of other cool chemical analysis as well. So one thing we've been doing with optical tweezers, this is the only thing I'll show you, for now, is we can determine the morphology or the structure of a particle. So if it's just one phase, homogeneous aqueous salt droplet, this is what the spectrum will look like. But more and more atmospheric chemists are finding that particles tend to phase separate. And so often you will get a shell of, say, organic carbon oil around the aqueous phase. And we can determine this structure from this structure because it changes the whispering gallery mode pattern. You can also get a third structure, which is where the second phase, like oleic acid, which is the main component of olive oil, it balls up on as this lens that floats on the surface of the aqueous phase. It's called the partially engulfed morphology. And you notice now in the spectrum, those whispering gallery modes, those sharp peaks are gone because we broke the symmetry. So now we can't have that optical cavity, that resonator effect anymore. So we can distinguish between these three different morphologies. Why are we spending all this time figuring out morphology? This seems like a weird thing to do. Well, if I'm a molecule like N2O5 that we were talking about before, I really want to react with the aqueous phase where the water is. I want to hydrolyze with that water, the blue phase. If there's a shell of organic carbon that doesn't contain water and I try to react with the aqueous phase, I'm going to have to diffuse through this thick organic shell. And that's really going to shut down that rate of reaction, which is important to understand. So that's why we're interested in morphology. And we've done lots of experiments on all sorts of different particles. And the bottom line is that the core shell morphology is actually very predominant under a lot of different situations. So it's important to be aware of because this has dramatic implications for the reactivity of particles and how they drive chemistry in the atmosphere. And this partially engulfed morphology, although it's kind of funny and cool to think about, it actually doesn't happen really much in the atmosphere. So you can sort of simplify your life and just think about these two, homogeneous and core shell. Okay. Even though I've probably gone over time, I would feel very remiss as an aerosol scientist during a pandemic, global pandemic that is driven by an airborne virus, COVID, to not say something about COVID. So finally, the CDC has acknowledged that COVID is spread by airborne transmission. They haven't admitted that this is a major transmission vector, but if you ask the experts, pretty much all of them have now come on side with that. My PhD advisor, Kim Prather at UC San Diego, has actually been a really big force behind trying to raise the public's awareness and the government's awareness about aerosols as an important transmission vector of this virus. So the bottom line is wearing a good fitting mask is one of the easiest, most effective ways to protect yourself and others. Because if you wear a mask and you are infected but asymptomatic, you could still be infectious. And if you wear a mask, you are reducing the amount of aerosol that you are spreading out just by talking and breathing to the world around you. And then if someone else is wearing a mask, they're reducing the amount of aerosol that they are inhaling. So it's really important to have a good fitting mask and to wear it whenever you're around people, especially when you're indoors, because the aerosol has time to accumulate. There's estimates that an average person, just by talking and breathing, will emit 1 million particles in an hour. And so if you're in an enclosed space without very good ventilation, that can really expose other people to high amounts of potentially infectious aerosol. So what have we done with COVID? Well, we have a really well-equipped aerosol lab at Carnegie Mellon, and a big local hospital network came to us and said, what we're dealing with is when we have to intubate a patient who's very severely infected with COVID, we have to put them on the ventilator. It's a very nasty procedure. I hope I never have to have it done to me, where they put this long tube way down your throat. And then when they extubate you, when you've improved, that causes the patient to kind of go into uncontrolled coughing fits. And all this infectious aerosol is potentially going all over the place in this pretty small operating room. And so that's a real threat to the healthcare providers that are in this operating room. So they asked if we could help them develop an enclosure, this plastic cube that you put over the patient that would help to contain the aerosol after they intubate the patient or extubate them. So you basically put this over the patient, you do the procedure, and then you leave them for a little while and let the aerosol settle. The problem is that you have to have these holes, these openings in the enclosure so the doctors can get their hands in there and for the ventilation tube to come in, and the aerosol is just going to go out those holes. So when we started talking to them, we said, okay, we can come up with some kind of seals for those coverings, and we can also do some sort of active ventilation and like pump the aerosol out. And they said, no, we can't do any active ventilation because the FDA did an emergency use authorization and they forbid the use of active ventilation and suction. And we said, okay, that's kind of weird. So we'll figure out something with passive. And what we came up with is we tried one layer of literally plastic wrap over the openings, and then we cut some holes for the doctor's hands to go through because those are going to be necessary. And what we found actually is 2 layers of plastic wrap work the best. And so we did a bunch of experiments with our fancy aerosol instruments, and we found even without applying any suction, just putting these 2 layers of plastic wrap, even though we do have holes cut in them for the doctor's hands to go in, you can essentially trap all the aerosol inside when we generate aerosol of the appropriate size, and you only see, you know, a percent escaping. And now, of course, right when we were getting ready to submit this paper for publication so that other people are aware of this, because this is a really low cost, effective device that, you know, developing nations could use. You don't have to have a pump around or anything like that. Of course, the FDA changed its minds and now they mandate that you have active ventilation and suction. So we have to do more tests, which are ongoing right now, and show that it also works under active ventilation, which it should. If it worked under passive, it will work under active. And then we'll finally be able to submit that paper. And I will, you know, not say too much more about our frustrations with the FDA, but you can kind of imagine it's been a little annoying. All right. That is all I had to share. I hope you thought that was interesting. Happy to take any questions. I also want to just end by acknowledging my group at Carnegie Mellon because they actually, you know, do all the fun science. I mostly, in normal times, am trapped in my office and don't really get down to the lab much. So back when we were able to hang out together, this is our outdoor look on a nice summer day at Carnegie Mellon, and then our indoor look next to the optical tweezers that we built in the lab and do a lot of experiments in. Also had a lot of great undergrad students work in my lab over the years who have really contributed to a lot of our research and papers. So I will wrap up there, and thanks again for having me.